Hello, and welcome to this presentation on set-type belief propagation with applications to SLAM. My name is Henk Wymeersch, and today we will explore how set-type belief propagation extends conventional methods and how it can be applied in SLAM. This work is a collaboration between multiple researchers and was led by Hugh Kim. Let's start with a brief overview of conventional belief propagation, or BP. BP is a method widely used for efficiently computing approximate marginal densities of variables of interest. It is based on a graphical representation known as a vector graph, which allows for message passing between nodes. An example is shown of a density function with two variables and three factors. In the BP method, messages flow from variable nodes to vector nodes and vice versa. And these messages represent functions of the associated variables. There are standard rules how to compute these messages involving simple sum and product operations. The marginal density of a variable, known as the belief of the variable, is the product of all the messages received by that variable node. BP has widespread applications in areas such as signal processing and communication, with the well-known methods such as the Kalman filter being explainable through this framework. Conventional BP operates on densities defined over vector random variables, such as multivariate Gaussian densities shown in the figure. However, in some signal processing applications, we deal with set random variables, where both the number of elements in the set and their order are random. So the set variable has a probability of being empty, a probability of having one element with an associated density, and a probability of having two elements with an associated density, and so forth. In these densities, the order of the elements does not matter. For example, in SLAM or target tracking scenarios, we may not know the exact number of targets, and the objects we are tracking may not be ordered. This randomness makes set random variables a powerful tool in some signal processing applications. Set-type belief propagation extends conventional belief propagation to operate over set densities instead of vector densities. In this method, we consider a set density, its factorization, and a corresponding set vector graph. An example involving two sets and three factors is shown in the figure. This example could, for instance, relate to the change over time of a set where Fa is a prior, Fc is a set transition density, and Fb is a set likelihood function. The message passing rules become slightly more complex, involving set integrals and sums, or products of set densities. However, the overall principle remains the same. Information is passed between nodes in the graph, allowing us to compute approximate marginal densities in the context of set random variables. Set-type belief propagation has a wide range of applications, particularly in sensing, where random finite set or RFS are common. In these scenarios, the number of sensed objects is unknown and modeled as a random variable, and the number of measurements per object is also at random. Additionally, objects may be misdetected and measurements may be due to false alarms. RFS theory provides a natural framework for addressing these uncertainties, but it is known to be challenging for newcomers. Set-type belief propagation offers a simpler, more accessible way to develop approximate and fast inference methods based on RFS theory. Our approach matches the performance of the best-known methods from the literature in selected SLAM applications. In conclusion, set-type belief propagation extends the conventional belief propagation framework to handle random finite sets, making it an effective tool for applications like SLAM and target tracking. The method simplifies the development of complex RFS-based algorithms while maintaining high performance. For more details, you can refer to our work published in IEEE Transactions on signal processing. Thank you for watching.